Well, we've got a pretty good chunk of our audience who's joining us and ready to go. So I'm going to go ahead and start with an introduction and give folks a few more minutes to join the room. But good afternoon to everyone who's joining us. My name is Nathan Dorr, and I'm the curator here at the Draper Natural History Museum here at the Buffalo Bill Center of the West in Cody, Wyoming. I'm joined today by our assistant curator, Corey Enko, who is joining us from the back end behind the scenes with the technology today. Thank you all for joining us for today's virtual lunchtime expedition. We've got a really full house and couldn't be more excited to have everyone joining us, especially today's speaker. I want to mention that support for the Draper's Lunchtime Expedition series has been made possible by the Sage Creek Ranch and the Nancy Carroll Draper Charitable Foundation. These sponsors help make these programs possible, and we're also grateful to you, everyone who joins us in our virtual audience, for your attendance, your feedback, and your support. We are recording these lectures and uploading them to the Draper's YouTube channel. So if you've missed any of the previous speakers, you can go and find their presentations there. In addition to those of you joining us via this Zoom webinar, we are also broadcasting today's presentation over on Facebook Live. Whether you're joining us here on Zoom or Facebook, please feel free throughout the presentation to submit questions using on Zoom the chat or the Q&A feature. Or if you're over there on Facebook Live, feel free to share your questions in the comments. We'll relay all those questions to our speaker at the end of the presentation. Today, we're fortunate to be joined by Dr. Chris Geremia. Chris is the lead bison biologist in Yellowstone National Park. He recently led his team in establishing a transfer program that has returned live Yellowstone bison to Native American tribes as an alternative to slaughter. His team is responsible for conserving bison within the park, studying bison demography, genetics, and their role in engineering grassland ecosystems. The team also works to reduce conflicts that occur when bison migrate out of the park. Chris earned his PhD in ecology from the Colorado State University and has worked as a member of the bison program in Yellowstone since 2001. Please join me in welcoming our April Lunchtime Expedition speaker, Dr. Chris Geremia. Chris?
Hello, how is everybody? I'm just sharing my screen and we'll get started here in just a second. So I'm coming to you from Mammoth Hot Springs, which is at the north entrance of Yellowstone Park. I'm in one of the historic buildings that the military used to live in, which is where my office is in the park. And what I'm here to talk to you today about is how bison in this park, or what we're learning about how bison in this park engineer the grassland ecosystems through their grazing. Now, kind of diving right into it, we all know the story. And once upon a time, even just 200 years ago, there were upwards of 30 to 60 million bison that roamed across the continent. In the blink of time, they were reduced to 200 to 400 animals. Now, some of those animals lived here in Yellowstone continuously. We brought Yellowstone bison, or we brought animals into the park, started a captive breeding program, and over the course of 100 years have restored a bison population here in the park. When you look across the continent today, there's about 400,000 bison in Canada and the United States. Now, the overwhelming majority of those are managed for meat production. They live in private preserves. A small number, about 20,000, are managed for conservation purposes, spread across about 60 different herds. On this map, it shows the Department of Interior herds, which constitute Park Service lands, BLM lands, Fish and Wildlife Service lands. And when you look at this map, it's pretty interesting. The purple shaded icons are fenced areas. You know, the green shaped icons are areas where bison, you know, have a little more space to move, you know, but all bison are constrained to some extent, whether by fences or by, you know, by other methods. You know, the other thing that this figure shows you is the sizes of these herds. Most are 100 to 500 animals. You know, here in Yellowstone, we have, you know, 10 times that, about 5,000 animals moving across the park. And back in the late 90s, I believe it was, Alan Knapp, you know, kind of wrote one of the first seminal bison papers talking about bison as ecosystem engineers. A lot of his work kind of focused more in the, you know, the middle area of this map, where we have smaller bison populations on tall grass prairie, which is a highly productive area. And, you know, his and his co-workers' work, and I follow their work still today, it's incredible. But one thing that always stands out to me is that, you know, one of the lines is in his initial paper was that, you know, the pre-colonial force of bison, their migrations and fire are gone. And his team has firmly believed that these forces of bison and fire acting against each other, you know, acted with each other to really shape how grassland systems worked. We're here in Yellowstone. It's a different system. It's not a fire system. And we have the opportunity to see probably, you know, the pre-colonial force of bison moving across a vast landscape, at least to some extent. You know, there's probably more bison in the park today than there was at times in pre-colonial times. As I said, there's over 5,000 bison that move across this park. Animals travel on average about 1,000 miles over the course of the year, making long distance migrations that span more than 70 miles of the park. So back in 1901, there was 20 animals in this park. They lived down right where my white cursor is, in this blue area here. I was in the Pelican Valley. They lived there because people really didn't know that they were there. We then started a second population where we brought in 21 other animals to the buffalo ranch. We built some fenced pastures, we planted hay grasses, we irrigated, and essentially started the early 1900s with a little group of captive bison right here and a group of wild bison down here. And over the course of the next 30 years, you know, here we tried to, you know, teach these bison what to do. I don't know, who knows what they were supposed to do. But in the wintertime, we'd round them up, feed them hay, keep them in a fenced area. In the summertime, we'd haze them on horses and try and push them to the higher country. We actually built fences in this area of the park to try and keep them out of this area while we were growing hay in the wintertime. At the same time, the native herd would migrate up to this higher country area in between where the captive breeding was happening and where they spent winter. And I'm going to show you a couple of these maps because it's, you know, there's nowhere in the world where we actually have learned the story of an animal relearning its migration. So this is an unprecedented story. So on these maps, the light blue represent where a herd or a breeding unit spends summertime. The blue represents where they spend the winter. And the arrows kind of showing their general migration distances. In the 1930s, when the captive breeding program was going really well, we took trucks, you know, and my cursor's following a road, but we took a truck and moved some animals. I just realized I have a laser pointer. How cool. You know, we moved the animals right over here and we dropped 37 animals in this part of the park. And we dropped another 36 animals in this part of the park. And very quickly here, the reds show the summering area and the greens show where they spent the winter. So very quickly, the animals learned to aggregate together in the summertime, and in the wintertime, they'd split into two different wintering areas. So middle 1900s, we had two herds of bison. One herd was a mix of the native animals and the animals we brought in. They learned to use the same summering areas, and then they split up in the winter. And I have no idea if in the winter, the native animals were down in the bottom and the introduced animals were up here. We didn't know that. And then this herd was started purely from the introduced lineage, because we took them from what was living here. And then as we moved through into the later 1900s, the 1980s, 90s, things started to change as the bison population was growing. First off, the animals that were summering here, we now call this the northern herd of the park. Again, it began during the winter to learn to migrate further and move towards the northern park boundary. And then in the summertime, they would return to the high country. The animals that used to winter in this area of the park, what we call the Pelican Valley, some still went up onto this high country in the summertime, but as this central herd began expanding, they began mixing, and this purple is supposed to represent a mixing of this northern and central herd, so that in the wintertime we'd have these dynamic movements of animals that are in the northern part of the park into the central, and then moving here in the summertime to breed. And as we get into the most recent part of history, and this we know for a fact because we finally put radial collars on animals during this entire time frame, and we could figure out just how animals were moving. The other ones were based on aerial observations of flying the park once every couple months and just seeing where the groups of bison were. So we were, estimating who was where and whatnot. We kind of see the pattern that we talk about today. There being two herds in the park: a northern herd that migrates along the northern gradient of the park, and a central herd that migrates throughout the central interior of the park, grouped up here in this red area in the summertime, and then in the winter dispersing to a number of different areas, including now the northern area of the park. All of these movements mean that bison travel upwards of 70 miles from where my pointer is right here to where my pointer is in this part of the park. And in doing so, they make very back and forth movements along the way, traveling more than 1,000 miles in the process. When animals started exiting the park, it created a ton of controversy. People thought the park was overgrazed. I think that's because we often don't think of bison as a migratory animal, because there's not many places where we're actually testing if bison can be truly a part of ecosystems, truly unfenced, truly allowed to roam. Migration is this idea that as this animal relearns a landscape, they move in tempo with seasonal patterns of resource availability. So when the resources are good in one place, they learn to move there to take advantage of those resources. And when they're bad in another place, they learn to move away from those. So as the bison relearn the land, they realize that there's some great opportunities if you migrate down out of the park in the wintertime to avoid deep snow. And the rest of this talk is going to be about what they do in the summertime. The forage maturation hypothesis is one of the, those general ecological principles. If you're an herbivore, it's the idea that your best diet, your best ability to put on weight happens when you balance the quality of your forage with the amount that you take in. So you want to get enough good forage. Not necessarily the best quality forage that's out there because it's there in low quantity. So you're balancing quality versus quantity. And research has repeatedly shown that this happens when plants are in their early to moderate growth forms. As plants first emerge in spring, they're highly nutritious and they're highly digestible. So animals get a lot of good energy out of that plant. But as that plant ages, it becomes more indigestible. There's more fiber and lignin and things that they must digest in order to harness the good energy out of it. So they don't get as big of a bang for their buck. The green wave hypothesis is really how this plays out across a migratory landscape. It's this idea that as waves of spring move up either latitudinal gradients, as shown in this picture here of moving from lower to higher latitudes, this wave of green spring, or in mountainous environments like we have here, from lower to higher elevations, animals should move in tempo with the emergence of plants in order to maximize diet quality versus quantity. I'm going to talk about Ndvi for a while. So I'm just going to take the assumption that nobody here knows what Ndvi is, when really probably everybody does. Ndvi is the normalized difference vegetation index. What it's really measuring is how green does the land look. So whether you do it from a camera, this is a member of somebody on my staff taking a picture of the ground and seeing how green it is, or whether it's done from a satellite, you're essentially measuring the same thing. You're looking at different wavelengths of light and ratios of those different wavelengths of light, which tell you how green the land would look to the eye. And there's a very predictable pattern that happens. In early spring, the ground is not green. As spring starts to turn to summer, it greens up very, very quickly. In early summer, it hits a point where it's as green as it's going to get for the entire year. And then as you start moving into fall, it turns yellow and gold, and eventually brown by early winter, so not green at all. Going back to the forage maturation hypothesis, if the amount of plant material that is in a spot correlates with how green that spot is, moderate values of Ndvi should correspond to when diet quality is the best, when you're balancing quality versus quantity. So on that graph, this would be the midpoint, the moderate value of Ndvi. So this should be when, whether you're using a camera from the sky or satellite, or just from 3 feet off the ground, when you reach this moderate point should be when the diet's the best for an herbivore. And doing some math, and this is what a lot of people do when they're going to go analyze spatial data, is you look at the rate that this curve is changing, this Ndvi curve is changing. You want to know when the slope of that curve is as steep as it possibly can be. The slope of this Ndvi curve, let's just call that the instantaneous rate of green up. It's a measure of how fast greenness is changing, how fast the land is greening up. This midpoint is when it's absolutely greening up the fastest. So what I'm going to talk about next is, are animals seeking this point out? Are they trying to, as they move across this landscape, get to places at the same point that is greening up as fast as it possibly does, which should be the time when they would receive the best diet? So the first thing we went out and did here in the park is we tested to see if diet quality was maximized at the peak instantaneous rate of green up. I'm going to use the term IRG, which means the instantaneous rate of green up. So does that actually happen? So we would go out to a location and we would clip the plant community at this level. And then we'd clip it here on the Ndvi curve. And then we clip it right here. And then we clip it after. And we would measure how many days were we from when we clipped it to when that actual location was at peak IRG. And when we looked at the nutrients in that plant tissue, we found that nutrient content in terms of balancing quality versus quantity, quantity versus quality, was maximized right at peak IRG, and it declined as days increased after peak IRG. So as you move from the blue to the yellow dot on this figure, diet quality declined. The next thing we went out and did, and this has been done in waterfowl, it's been done in large mammals, it's been done in a number of different terrestrial species and avian species, trying to figure out, is there a general pattern of animals tracking the green wave? The short answer is yes. I'm going to go through a series of figures now as we go through this. So all of these dots represent when bison arrived at a location along their migratory route. These data show more than 64 bison collared over I think it was a 15-year period. So it's going to be some of the same animals monitored over years. There's a lot of noise, a lot of variation in this data. But the x-axis represents when an animal got to a point on its migration route. The y-axis represents the date that that pixel maximized its IRG, when it was greening up the fastest. So if an animal was tracking the green wave, surfing the green wave, every location should be right along this 1-to-1 black line. If the points are on this side of the line, you're in front of the green wave. You're getting there before spring happens. If you're on this side of the line, you're getting there way after spring happens. Now you're going to expect a lot of slop in this information, some spread around the data. But when you fit lines to all of these points, you see that bison start spring maybe just a smidge in front of the green wave, but they're generally tracking, they're moving in tempo with it. They're getting to locations as the green wave is getting to those same spots. I'm just going to build on that same figure. But then as you get into the middle spring periods, and the bison are increasingly falling behind the wave. And as you get into the late spring periods, the latest spring periods, they've let the green wave go by. They're arriving there well after green up has happened. And these same colored points correspond really well to, this is us, roughly 60-mile migration of a single bison. When the landscape was greening up, these green dots indicate when that animal was getting there, roughly when the green wave was hitting that spot. So bison start here in the wintertime. This animal was moving, and all of these green dots suggest that these movements were roughly in tempo with the green wave. And then as the animal got to its mid-elevation areas, you see that these brown dots start happening. These brown dots show that the animal's getting to locations, the green waves moved on. You're down in this area where the animal's getting to locations well after the green wave has gone there. And you see by the time the animal gets to its highest elevation areas, it's months behind the green wave. This doesn't really make a lot of sense. Why would an animal start with a particular movement strategy and switch? So we went out and we were tracking these animals as they moved. And now, rather than collecting the plant material, we were collecting their fecal samples and trying to identify what was the quality of the food that we found in their fecal samples. And this dotted line corresponds with when we collected a fecal sample from a bison in a foraging spot when it was at peak IRG. And all of these dots out to the right are when we collected a bison when it got to a spot well after the green wave, a month after the green wave. Out here is 2 months. Out here is almost 3 months after the green wave. And this gray area on this plot represents generally for bovids, for bison, for domestic cows, the ratios of nutrients and poop when their diet is optimized, when they're getting a lot of good energy. So this doesn't make any sense with what we just learned about bison movements. What we're finding is that bison only begin to optimize their diet as they start catching or moving with the green wave. But they seem to find this way to maintain an incredibly high diet as they let that green wave go by. Let's just take a little walk around the bison migration for a second. So right now we are in early spring. We are right about this location where this blue arrow is. Now, this is the type of plant community that these bison grazed intensely through in very early spring. This picture was taken in early summer, long after the bison have left. Where I'm going to step into next is a field exclosure experiment that we set up, which I think identified what's really truly going on here. This field experiment had several levels of treatments. The first thing we did is we set up sites all along the migratory landscape, from areas bison used in just early spring to areas that bison used in tune with the green wave to areas that they used well after the green wave had passed. These areas represented different grazing intensities. Within each site, we set up plots that just measured the actual conditions, the grazed landscape. Then we set up controls. We put up these small exclosures that prohibited large mammal grazing for the entire grazing season. We also had different treatments that excluded grazing for short periods of time, like 30 days or 60 days, to see how that affects, see how plants were growing different rates throughout the growing season. Anyway, the point of this figure is early on in the season, you can't tell that thousands of bison migrated through this area and essentially ate most of the plants that were growing. However, when we move into summertime, we move further along the migration route. Now indicated in this little figure in the bottom right, this is where bison are now moving at first in tune with the green wave and then falling behind. And a couple of things that are happening. As bison fall behind the green wave, the animals also group up to form massive aggregations. Sometimes we see 2,000 to 4,000 animals, in these aggregations during this time of the year. Animals are also returning, as you can tell from all these dots concentrated next to each other, returning to regraze places they've been to before. As a result of these things, when you go out and look at this same field site, there's a dramatic difference between the forage or the plant community conditions inside the exclosures to the control conditions outside the exclosures. But one thing that jumps out to me immediately is, my gosh, outside the exclosures looks like those moderate conditions, the moderate biomass conditions that the forage maturation hypothesis would say corresponds to the best possible diet when you're maximizing quality versus quantity. So we went out and measured plant conditions inside our controls versus in the grazed grassland. And this plot on the left shows those plant conditions. This is in those higher grazed sites where animals are aggregated into big groups. They're returning to regraze the same places. The grazing intensities are high. The blue dots show the diet quality conditions in the grazed grassland. The gray dots show the conditions in the controls. And what we see is throughout most of the latter half of the growing season, after the green wave passed, grazing is enhancing diet quality. It's providing animals the same sorts of foods they would get as if they were moving in tune with the green wave. And as you move across this multi-panel figure from left to right, now you're down to your low intensity sites and you're not seeing those differences. If the bison aren't doing this massive pattern of grazing and synchrony together, they're not having, you're seeing what you saw in that first figure that I showed you. You can't see a difference in the plant community inside and outside of those exclosures. And it got me thinking over time, as whether as I was flying in a plane, surveying the animals in the park, or whether I was, riding across these migration routes or going out to these grazing sites. It was like, my gosh, it just feels like the entire way this park greens up, the entire way that the plant, the greenness changes, the quality of the diet changes throughout the year is fundamentally different, at massive scales, at the landscape scale, because of how bison are using it. We had this really cool opportunity here in the park over the last 20 years. Those original figures that I showed you of bison relearning migration routes, there's generally two different herds. There's the northern herd in the northern half of the park, the central herd in the central interior of the park. Well, the central herd decreased from a high of over 3,000 animals down to about 1,000. At the same time, in the northern part of the park, that herd increased from several hundred animals, 600 to 800, to more than 4,000, setting up this incredible natural experiment. Where in one part of the park, the population went way up, the other part of the park, it went way down. We wanted to know what was the effect. we could look at the same sites over time and see how did the Ndvi curve, how winter turned to spring to summer to fall to winter, how did that progression change as bison and density went up and down? And moreover, we use GPS collars and field measurements to relate, bison, a population size and GPS collars to actual consumption rates on the land. The bottom line is, as bison graze sites more intensely, changed the entire way that spring came to the park. We found that looking in the same site, areas began to green up earlier. So this lighter green curve is what Ndvi, or the greenness of the land, looked like with bison, a lot of bison. This is what it looked like with a little. Greened up earlier, it greened up faster, it became more green overall, it reached that peak sooner, but it stayed green longer. So the entire way that this green wave that you can see from space was moving across, coming to and moving through the park, is fundamentally different because of this massive herbivore. This is this is a part of the northern range. This is the Lamar Valley. The bison migratory landscape moves across, 50 more miles of what you can just see in this picture. And I wanted to look at the same sites. I'm still talking about that last analysis I was talking about, and saying like, okay, now let me try and identify the factors controlling how, the shape of the Ndvi curve, the curvature, the how fast it greens up, the how long it stays green, the when does it brown down. So looking within the same site, we looked at how grazing intensity, snowpack, rainfall, temperature, aspect, all influence these year-to-year differences in the same site. The higher up you are, when you're bio 1, you're the most important factor controlling the shape of the Ndvi curve. As you would expect, temperature early in the growing season. But this just blew me away. As you get to the time when bison are falling behind the green wave, they become the most important factor driving how green that landscape is. More so than rain, more so than temperature, more so than snow. And you look for almost the 3/4 of the growing season, their grazing is one of the top 2 factors controlling what that land looks like. A lot of what I just talked about, and I'll acknowledge it at the end, but just in case people take off before I get to the acknowledgements, was a paper we put in the Proceedings of the National Academy of Sciences 2 years ago, I think now. And please, I encourage you to go there to get more details, or if you're really into the science of it. We made that paper available to anybody. So, you don't need to be a member of the society or anything. And that paper had, massive reach. And it tells us a lot about, there's not a lot of places to look at where bison are actually still a migratory force of nature. And it gives you some sense of what's possible when they are. And it gives you some sense of what we should be thinking about in terms of large landscape conservation and bison into the future. Some of the rest of this talk is going to be about some of the more recent work that we're doing that builds off of exactly that. It's not as vetted, but I wanted to take this opportunity to share with you, like, what are we doing right now and learning right now about the next step of bison and ecosystem engineering. Generally in an arid place like Yellowstone, and you look at some of those pictures, Yellowstone's not an arid place. It's soil moisture and soil nutrients basically limit plant growth. Let me step back one step. I always used to tell this story when I would give talks. I was in graduate school at Colorado State University. I was in a seminar, and we were watching this video about undergraduate students at, I believe it was at Princeton, and people were asking them questions. It's like, well, what where does the material in plants come from? Does it come from elements in the air, or does it come from nutrients in the soil? And the answer they were trying to get you to say was elements in the air, because through photosynthesis, plants absorb carbon dioxide. They fix that carbon dioxide into sugars, which becomes the building blocks of energy in the ecosystem. That aside, nutrients play an important part of the story here in Yellowstone. So plants absorb nutrients predominantly through the soils. It's not through their leaves. They also absorb moisture through the soils. And they face this trade-off. In order to absorb carbon dioxide from the water, from the atmosphere, they need to lose water in the process. So trying to get carbon dioxide in, water goes out. That's a trade-off a plant faces. That controls how fast and how much it grows. At the same time, plants need soil nutrients to convert those simple sugars into more complex structures. So if those soil nutrients aren't there, plants also stop growing. Now, it makes a lot of sense that grazers can modify, or start, manipulating how the system works here, the factors that actually control plant growth. This is a picture of the Lamar Valley on the right, just to give you a sense of what a grazing lawn can look like. There's not tall plants waving in the air. The plants are held in really low stature. When plants are really low to the ground, it could improve their water use efficiency, because the microclimates down around the ground are more humid than if the plants are tall. So when they are absorbing carbon dioxide, less water is lost, and as a result, more water is maintained within the soils, which may give the plants an opportunity to regrow. Bison also return an immense amount of nutrients to the soil in the form of urine and in the form of dung. The decomposition rates of animal waste is much more rapid than the decomposition of plant litter. As a result, grazers, by converting plant tissue into animal waste, those nutrients can be recycled back into a plant available form much more quickly than they can if that source was coming from plant litter. And finally, we showed in the surfing work that we did, or the surfing and then not surfing work that their grazing can improve leaf tissue quality, the amount of nitrogen in leaf tissue. How does that happen? A lot of plants tiller in their response to grazing or being clipped. What does that mean? So a plant has meristematic tissue, and it can regrow from where there's meristematic tissue. That meristematic tissue can be above ground on at a branch in like a grass blade, or it can be at the crown of the plant, which is that area right above and below ground where most of the blades emerge from. So when a grass gets bitten, it can grow a new shoot off of the crown. And it does that because, my gosh, where I was just growing, I just got predated upon. Let me try growing somewhere else where I may not be predated upon. So, that constant production of new shoots, those are those early spring shoots that produce such high quality shoot nitrogen. Now, there's obviously interactions between all of the above, because if bison can improve shoot nitrogen, well, nutrient-rich shoots make nutrient-rich poops, which then makes nutrient-rich soils for the plants to continue to absorb more nutrients. And when you add more soil moisture, there's more opportunity for soil nutrients to be converted from a plant unavailable to available form. What we really wanted to test was what's going on in this picture that I'm looking at. What I see is really short grasses, really tall grasses. Plant communities have a very important role to this ecosystem. Through photosynthesis, they harness sunlight energy and then convert that into a form that's usable to herbivores, and from there it can be transported through up the food chain. So the amount of herbaceous plant material, the amount of forbs, flowering plants, and grasses that's made each year in the ecosystem it's a very important ecosystem service. We wanted to find out, were bison inhibiting that ecosystem service? Were they decreasing plant growth, for their own gain, for making higher quality? So I forgot this slide, one last step. Before I go further, this is really important to understand. Because bison are migratory, and this is a migratory landscape, they create a pattern of different grazing intensities throughout this entire park. This is a heat map showing their hot spots versus cold spots during the entire growing season, all the way up to when snow falls. Because bison are moving rapidly in tempo with the green wave. They're aggregating into big groups. They're returning to regraze the same places. There are these hot spots on the map, but there's also a ton of cold spots, so the timing at which plants are being grazed, the intensity, the regularity, the amount of return movements, bison are creating this heterogeneous landscape based on how they graze it. That enabled us to fit up, to build a stratified experiment. We first identified sites that are generally resource rich, lots of soil nutrients, lots of water. Resource poor, not a lot of soil nutrients, a whole lot less water. So basically, rich sites are your productive sites, poor sites are your less productive sites. Then within each of those, we identified areas of high, moderate, and low grazing. And we wanted to see, research out of the Serengeti, research in other grasslands, research in other bison areas have shown that resource rich and resource poor sites respond differently to different levels of grazing in terms of, is the plant community able to compensate, able to keep up with bison grazing? What we found was absolutely here. So starting on the left site, these are your resource poor sites. The red dots represent the amount of plant material that was produced during the whole growing season, accounting for offtake. The blue represent the controls. This would be the stratification of low grazing. We found no support that grazing lowered productivity. Going to moderately grazed sites, the same thing. We found no support that grazing lowered productivity. Going to highly grazed sites, the same answer. So the bottom line is the plant communities were able to regrow into response to all of these different patterns of bison grazing. Going to the resource-rich sites, the same trends happened. In fact, these p-values closer to 1 would suggest the exact opposite of our hypothesis was going on. In fact, there was support that under some levels of grazing, or more support under some levels of grazing in resource-rich sites, plants were not only able to compensate, but they did better under bison grazing. We wanted to be sure. So the next thing we went out is we went into a resource-rich site. We went into a resource poor site. We built 20 meter by 20 meter pens. Within that, we did a stratified clipping experiment where we clipped different plots at low, medium, high intensity. We clipped that plots only early in the season or only late in the season. We tried all of the different things we've tried to do in livestock grazing to identify what's the best practice. The bottom line is we always found the same result. These areas produce the same amount of plant material. They're able to compensate to manual clipping. Then we took the next step. We extracted grasses here in Yellowstone, brought them to Washington and Lee University and started growing them in greenhouses and tried clipping them at different intensities and seeing how plants, allocated above ground and below ground growth in response to clipping. Some put on more roots, some put on more above ground matter. The bottom line is it was the same story. Across the observed grazing intensities that we have here in the park, plants were able to compensate for the herbivory that was happening. And that's a really important concept. That means although things look very different, whether you put an exclosure out there and what's inside that exclosure or not, energy flow is at least sustained in this ecosystem. You're still collecting, harnessing as much of that sun's energy and making it available to flow up through this ecosystem. But I really think that's just that was a whole lot of work and a whole lot of experimentation to really just get started on what's the next step. So we've shown that bison changed the way that spring come to this park. I feel very confident that bison don't lower the productivity of this landscape. Now, as Professor Knapp, and it's funny, when I was at Colorado State University, I got to listen to him speak. I never told him that I was the bison biologist in Yellowstone, but I was really blown away by his beliefs and his thoughts, and his entire work group. Bison, I believe in this migratory context, are having these massive knock-on effects to this ecosystem. And it all comes back to this concept of migration. And if you look in the lower left, bison are a heat map, a disturbance map, whether it's like a wildfire that's got hot spots and cold spots in areas it doesn't burn, it's changing the land. Bison are doing the same sort of thing across a landscape the size of Rhode Island. This is a big place. So let's key in on the things that bison affect: soil moisture, nutrient availability, leaf nitrogen content, or the nutrient content of the plant tissue. So these plots on the right are continuing that same stratified experiment, which I was talking about, where we've got resource-rich sites, we've got resource-poor sites. We've got areas that are controls where we've excluded grazing for the entire year. We've got areas that are actively grazed. We've got a further stratification of high, moderate, and low grazing. So where these pluses occur on this biplot is showing at points in the growing season, at 30 days into the growing season, at 60, at 3 months, at 4 months, at 5 months into your growing season. So when plants start to emerge to when they're completely golden brown and dead at the end of the year. What is happening to these ecosystem components where nutrients are stored in this system? Well, in rich sites, we see that in almost all levels of herbivory, but particularly the moderate and high herbivory, they're changing the content of nutrients that are above ground. That's a big deal because those content of nutrients are available to all sorts of different animals in addition to bison. The same story for soil nitrogen. That's a big deal because there's a lot of things below ground that are seeking out high quality, soils that are nitrogen rich. The next step, soil moisture. There we didn't see the same effects. So it really, bison more so seem to be altering the nutrient flow rather than the water flow in this system. And the plot on the right just show the same sorts of findings for resource poor sites. And this makes a lot of sense to me. The differences between these two graphs is that resource poor sites seem to, the feedbacks, the knock-on effects on nutrient composition and where they're stored, seem to be stronger under lower to moderate grazing versus in the higher sites under higher grazing intensities. So these things control many things in the ecosystem, including what plants grow there. We've gone out to all of these different sites and tried to look at the composition of the plants in the plant community. This is an ordination plot. It's a typical community ecology measure. Basically says, like, if I take an entire matrix of gibberish of what plants and what's their relative abundance in the plant community, let me mush all of that variation into just two simple axes, an X and a Y. We see that our resource-rich sites generally fall on one area, and which are the green and the pink, and our resource poor sites have different plant communities, falling in the orange and the blue sites. So if I just focus in on one of these, let's just say this, this green type of plant community. So all of the plant conditions are roughly the similar here. We find that bison, or it seems like there is variation in that plant community amongst the functional groupings of plants that we find there. When I say functional groupings, it's going to be how long that plant lives. Is it an annual versus a perennial? What's the life form? Is it a graminoid or is it a forb? And what's the rooting depth? Is it shallow, medium, or deep? And what's the reproductive strategy? Are you a bunch grass, which has to seed in order to make it, a new plant? Or are you a rhizomatous grass, the type of plant that can put a root underground and then pop up somewhere else? Kind of like a strawberry, even though strawberry is stoloniferous, that root's above ground. So when you look at these functional traits of plants, they vary predictably with how intensely that site's grazed. We see you move from sites, in this particular community where you've got a lot of bunch grasses, so with graminoid dominance, towards more shallow rooted forbs, so your small flowering plants, and then also your rhizomatous growth forms as you increase grazing intensities. These little lines, these topographic lines, show increasing grazing intensity. So it's very interesting. So what's going on here? Is it that, bison grazing has nothing to do with it, and it just happens to be that they're going to sites because of the plants that are there? Or is there something more to it? Are the bison actually driving the plants that are in those communities? Going out to some of these same grazing sites, which we've monitored, I shouldn't say we, some of our predecessors in the park, who did research here in the 80s and 90s, we could look at how these functional groups have changed in these same sites over time. And it lines up exactly with that last plot that I saw. These two sites are intensely grazed bison sites today. And we see that back in the 80s, they were dominated by bunch grasses. And today they're dominated by what you see in this upper picture with this big bull bison on a grazing lawn. Shallow rooted forbs, rhizomatous grasses. And we're seeing the same shift generally across these communities. And right now, this is kind of the edge of where we are right now. Are bison making this land, while maintaining its productivity, better for themselves? The same types of plants that prefer these high grazing conditions doing better, which then feeds back on bison. And what about some of the other communities that rely on these plants, the arthropods, the small mammals? We're trying to look at these knock-on effects of bison. Now, there's not a lot of places where we can give bison room to roam. There's not a lot of places where, I just said that, where this is happening anymore. The map on the right is the Hornaday map. It was, kind of the great constriction from when there were 30 to 60 million to 200 to 400 animals. These massive herds likely moved across this area. And granted, the research we do is limited to the edge of where the prairie hits the mountains. But I think there's a lot to apply from what we're learning. They likely shaped nutrient cycles across large landscapes, created this heterogeneous habitat, and really changed ecosystem, how nutrients move through systems, what species live there. They were truly force of nature. So when we move towards large landscape conservation, what we've done here in Yellowstone is some things we do is a bit controversial. Some of it doesn't make sense. Some of it makes a lot of sense. One thing that makes a lot of sense is it's telling us what we need to do if we're going to do landscape level conservation of bison. So with this, I just really want to acknowledge Bill Hamilton at Washington and Lee University, Douglas Frank at Syracuse University, Matt Kaufman in Wyoming, Jared Merkel at Kaufman in Wyoming, Mark Hebelwhite at the University of Montana, and the various National Park Service staff. We have a team. We're excited about what we're doing here. Thank you for the opportunity for talking about Yellowstone bison today and about something other than the controversy. And I think with that, we got a few minutes for questions.
Excellent, Chris. Thank you so much. Your presentation has generated lots of wonderful comments and questions. So again, for those of you watching via Zoom, you can submit your questions using either the chat or Q&A features below. Viewers watching on live on Facebook can share your questions in the comment section. So we have a few to begin. Have you seen, and you started to mention this, have you seen changes in soil microbes or invertebrates or other fauna due to bison grazing?
That really is right where we are right now. So we're trying to investigate, what are the effects on soil fauna, at the microbial level, at the arthropod level. What is the effect on small mammals? What's the effect on bird community composition? There's been reasonable, if you look across bison literature, those links are out there. But what we haven't been able to pull together, I would say to date, is when you have them as a migratory force in nature, what is the pattern process that's going on here? And not what is happening in an individual site, but how are they reshaping this ecosystem?
Excellent. Can this vegetation nutrient change be seen with cattle grazing as well?
That's a great question. I think that if you follow regenerative agriculture, I think one thing that's very important is that I was taught, wrongly so, that, agriculture is bad. You throw nutrients into the ground to get things to keep growing at an incredibly high rate. Or if you're a rangeland, you manage for very low, moderate, homogenized, uniform grazing everywhere. And those are kind of the two gold standards. And that's completely false. I think the science of livestock grazing and land management is evolving as the science of ecology has evolved. And an example of that would be regenerative agriculture. But really, it comes down to, animals will manipulate the system. But if you constrain numbers or inflate numbers or constrain how they can move, those effects, you're going to influence those effects.
Excellent. A clarification question. Bison move from low to high elevation from winter to spring, correct? Or low elevations in winter, high elevations in summer?
It's so distracting giving online talks where you see a little icon of yourself in the corner of the screen. I must have said the wrong thing. So bison move from low elevation in the wintertime to high elevation in the summer. In the park, that gradient looks like anywhere from 5,000 feet in the winter to above 10,000 feet in the summer.
And another question to kind of tag onto that. Will bison naturally, do you anticipate that bison would naturally move east? And if so, potentially how far?
The difficulty of moving east here is that the entire east boundary of the park is a mountain range, and bison tend to make exploratory movements in the wintertime, following the river valleys. So the major river valleys that exit the park are to the north and to the west. So that's the way that we've seen bison naturally, the land naturally encourage them to relearn to migrate. Now, I have no doubt that if this wasn't a national park, and the animals were taught, say driven to the east, and they realized there were better habitats there, they would do that.
Are bison effects on invasive plant species being monitored? And is intense grazing giving invasive plants an edge?
That's a really tough question, and that's a really good one. And I have this conversation all the time. So we specifically took the point of looking at the functional groups of plants, the functional traits of plants, rather than the names of plants here in the park. We started by looking at their taxonomic name, but that's important because many different plants can have a similar function on the ecosystem, on how, when they green up, how they absorb water, how they reproduce, all of those sorts of things, and some don't. So really the question is, are you changing the functional composition of the landscape? Are you converting it from, deeper rooted and moderate rooted graminoids to purely monocultures of shallow rooted plants that are only annuals? That would be an example of, what I'm talking about. So different types of invasive plants, have their own functional characteristics, and there's certain ones that I would say are bad for this ecosystem, bad for any ecosystem. And there's no doubt that if you make an area nutrient rich, it's going to be able to support lots of plants. So there's no doubt that there's different non-native plants that will come into areas that bison use. And what we're not seeing right now is that wholesale conversion to the functional traits of, communities that are now functionally not working.
Excellent.
Everybody wants me to say, are weeds going up? But if there's anything that I tried to talk about in this talk, is like, that's missing the picture. There's times when it's bad and there's times when it's natural.
Great. Are there analogous studies in the tallgrass prairie area of North America?
There are, and the difference there is, water, the growth forms of plants, their reproductive strategies, the level of bison herbivory, the role of fire, the amount of fire, and the amount of space. There's not many, and people may disagree with me. There's not an example on the tallgrass prairie, to my knowledge, where we've got the full force of bison back in action. They're in more constrained areas. So I would encourage you to reach out, starting with the work of Alan Knapp, and his entire work covers many people, Sam Fuhlendorf and others, to start learning about the tallgrass prairie. I think fire is more important there.
Excellent. From a bit of a different perspective, does Yellowstone National Park look at the archaeological data on migration in bison in the greater Yellowstone ecosystem to inform management?
That's a great question too. Gosh, I knew they'd get harder. The thing with bison is that there's some work that some folks are doing out of Canada that are trying to look at trapping records where people saw animals, going back into the 1700s, looking at trapping records, and use that to try and estimate where bison were. And they believe that as this extirpation was happening, 30 million down, 30 to 60 million down to a few hundred, and the bison were essentially pushed from the plains where they lived in highest abundance to the mountains, as refuge, trying to avoid these hunts. That was probably part of the story in the 17 and 1800s. Bison have been here since the last ice age in the park, which means through disease, times of climate change, natural climate change, the animal abundances and distributions likely changed massively, including, the role of tribes. So here in the park, what we care most about is ecosystem process. It's a place where we've restored the top dog, and now we've restored what evolved to combat the top dog. So wolves and bison pushing against each other in a natural ebb and flow, and both are affecting other herbivores, how plants grow, and structuring this ecosystem. That is our top priority, because there's not another place where we're doing it.
Excellent. One question that we've gotten in a variety of forms that I wanted to throw out, and I'll mention too that you've generated a lot of wonderful questions, and out of respect for your time and those of our audience members, I'm wondering maybe if I can send you these questions, the remaining questions, and have you answer them, and then we can put that perhaps in the description field of the video that we'll upload to YouTube, and then also on Facebook as well. But one I wanted to throw out there, and it was phrased, I'm wondering about what all of this means to bison management in the park. All of this begs the question, if from a strictly biological standpoint, should the herd size in the park be allowed to increase?
From a strictly biological standpoint, the herd size in this park could probably double. What we're testing here in Yellowstone is, can bison truly be wild and truly be a part of ecosystems? Can they be treated like elk and deer and pronghorn? And I don't think you can just turn that switch on. For 20 years, we've been slowly, it's more of like a dimmer on a light. For 20 years, we've been trying to slowly figure out, is society ready to have bison like a wild animal? And I think much more so today than 20 years ago, the answer is yes. But still, it's a slow, gradual building of trust in the local communities, building a trust in states and other federal areas that it's possible. And that's what we're really trying to do here. I can't wait to do another talk in 20 years and have the next map of where bison are and what they're doing.
Excellent. Well, Chris, thank you so much. Again, lots of really amazing, wonderful questions. I will share those with Chris and get some answers, and we'll share those all. Chris, thank you again so much for taking time out of your schedule to visit with us and to share your knowledge, your experience, and clearly your passion. Another big thanks to our sponsors, Sage Creek Ranch and the Nancy Carroll Draper Charitable Foundations, for their support for the Draper's Lunchtime Expedition series. Just a reminder that this presentation has been recorded and will be uploaded to the Draper's YouTube channel. So if you missed anything or would like to share this with someone, you'll be able to find it there. To our viewers, we'll be switching to an email distribution platform beginning with the May Lunchtime Expedition. So be on the lookout for that in your email inboxes. With that new platform, you'll be able to more easily share announcements with others. And should you desire to do so, you'll be able to easily unsubscribe. Again, Chris, it's been a pleasure having you join us today. Thank you so much. And thank you to everyone who has joined us. We look forward to seeing you all in May, on May 6th, when we are joined by Chris Linder and Dr. Rob Sohn to explore what lies beneath, exploring Yellowstone Lake's mysterious vents. In the meantime, be well, everyone. Take care.